Shalom, do you hear me? Welcome to Jerusalem. My name is Shlomai. And I can't tell any stories on Jay because I still need him to sign on my PhD thesis. So I'll focus on the structure. I'll focus on the structure of bimaterial ruptures. Ilya just presented us how much experimental measurements and understanding the underlying physics of sliding motion between two similar bodies is complicated. So we took this type of experiment and added some more complexity. We replaced one of the identical PMMA bodies blocks with a softer material with slower wave velocities, in our case polycarbonate. We still press the two blocks together, we shear them, and we get detachment, propagating ruptures, earthquakes in the lab. Okay, so this type of experiment is called bimaterial systems. Bimaterial interfaces are important. This is the general rule. Many interesting examples can be many natural faults, for which after many years of cumulative slip result in the fault being composed of two different types of rock on either side. Throughout this talk, I will mention a lot the homogeneous system to better understand and emphasize the uniqueness of the bimaterial systems. So the first very clear unique feature of bimaterial system is the up-down breaking, symmetry breaking, and which leads also to left-right symmetry breaking of the amount of displacements of the materials. While sliding, every material point moves. In the homogeneous system, the amplitude of the displacements of all the particles inside the materials are anti-symmetric across the interface, which keeps the normal stress constant at the interface. The bimaterial systems lack this symmetry. As a result, the normal stress vary with the slip. And the coefficient mu star is a function of the material contrast and of the rupture velocity. This variation is in addition to the applied compressive normal stress, which is negative. This is what's called bimaterial coupling, and it is a very important point to understanding bimaterial friction. And this is an elastodynamic effect. When considering frictional motion, the frictional resistance at the interface is proportional to the normal stress. If the normal stress varies, also the frictional resistance can change, and also the amount of energy dissipated while sliding. This is one of the motivations to investigate bimaterial friction. Here are some of the main contributions to understanding bimaterial friction. I'm very lucky to have some of the authors here in the audience. So I'll take advantage of Ilya's explanation about the experimental setup, and I'm presenting here some experimental results using the contact area. The x-axis are all the points along the interface, and this is the time-dependent development of a rupture. Hot colors are stronger contact area. So on the left, here is an example of a rupture in an homogeneous system propagating at the asymptotic velocity, which is the Rayleigh wave velocity. On the right, there are two examples of bimaterial ruptures. The only difference between them is the propagation direction. Okay? The propagation direction relative to the direction of the displacement of the softer material makes a difference. We define the positive direction when these two directions are the same, and the negative when they are opposite. The bimaterial coupling tells us that the normal stress can either increase or decrease. It depends on the velocity of the rupture. For subshear velocity regime, the normal stress decrease. The variation decrease, which means some release of the implied compressive normal stress, which makes the sliding easier. In the negative direction, we have an increase, which prevents the sliding. For supershear ruptures, the coupling flips sign. Now it is easier to slide in the negative direction. As a result, also these are typical examples of the rupture in each propagation direction with typical velocities. In the positive direction, here is a rupture propagating at close to the asymptotic velocity, which is the shear wave velocity of the softer material. In the negative, this is supershear rupture. Okay, so from now on, I'll focus only on the positive direction. We can zoom in into this dashed line to have better understanding of the dynamics of the contact area. Here is the contact area profile as a function of distance from the rupture tip. Ahead of the rupture tip, in the positive x-axis, we see no change in the contact area. Behind the rupture tip, in the negative x-axis, we see a drop of about 30% as a step function. This describes a fracture process. In the positive bimaterial directions, we have much richer dynamics. In front of the rupture tip, we have an increase of the normal stress. Then, when the rupture passes, we have a huge reduction, followed by a fast recovery to a residual value. The time scale of the reduction and the fast recovery is much shorter than the healing time for broken contacts. That means that the reduction, this contact area dynamics describes the dynamics of the normal stress at the interface. So actually here we start to see the unique bimaterial coupling which tells us that the normal stress can change at the interface. This reduction is the blue line here, you see, that doesn't appear in the homogeneous system. So we see the start of the bimaterial coupling, but we want to have a wider picture. So we add to this also the normal stress signals measured by the strain gauges located along the interface. We start with the homogeneous system. The black line is the signal 3 mm above the interface. The gray line is the signal 3 mm beneath the interface. They are clearly anti-symmetric, which means that the end to the interface itself, the normal stress doesn't change. In the positive direction, we see asymmetric signals when the larger signal belongs to the stiffer material. Let's follow it. In front of the rupture tip, we have an increase of the normal stress, which corresponds to the increase in the contact area. Then we have a very large reduction. Also, we see it in the contact area. These both signals within a few millimeters behind the rupture tip recover the residual values. We can also add to it the particle velocities to learn about the slip at the interface. We see that in the homogeneous case, we have long tails indicate on extended slip behind the rupture tip. This describes crack-like behavior. In the bimaterial case, we see now that the larger signal belongs to the softer material, which is highly localized in space in a pulse-like shape. This is for rupture propagating nearly the shear wave velocity, the asymptotic velocity. Actually, this is the first direct experimental observations of the coupling of the bimaterial. Ruptures with this strong coupling are usually called slip pulses. To have some feeling what it means, if you want to push a carpet, the efficient way to do it will be to lift it at the edge, create a wave of motion propagating along the entire carpet, resulting in the whole carpet moves. For me, it is easier to think about a caterpillar moving forward by pushing its end. So we were very happy to observe these ruptures. I'm still excited. I hope you too. But we want to understand them better. For this, we turn to theory. We use the boundary conditions describing our problem are continuity of the normal stress of the softer and stiffer material. In addition, we start by simplifying the problem. Though at the interface, the frictional resistance is proportional to the normal stress, here we assume once the rupture passes, it becomes constant. We use analytical solutions which considers the singular term, which describes crack, which dominates asymptotically close to the rupture tip. We have these solutions thanks to Mukhtar. Where is he? Hi, Toda. And usually, we have the numerical simulations, which solves the complete elastodynamic bimaterial ruptures. These simulations were conducted by Dr. Dave Kammer from Cornell. So let's start with the stiffer material. Here are all the strain components for ruptures propagating at different velocities, propagation velocities, up to the asymptotic velocity, which is the shear wave velocity. We use the XX component to fit the scale parameter of the solution to the experiment. This scale parameter also fits all the other components. So we have a very good description of the singular strength fields by bimaterial crack. What happens in the softer material? Here are the experimental measurements. And this is the analytical solution with the same fit parameter that we got from the stiffer material. We can clearly see we have growing discrepancies with increasing rupture velocity in both YY and XX components. To understand them, we add here also the numerical simulations. This is the red lines here. Here we can see much better agreement in the amplitude and the width. So the simulations capture the main features of the experimental observations for rupture velocities, almost the shear wave velocity. But let's have a closer look what happens at the shear wave velocity, where we observed the unique slip pulses. Here we have the stiff material, the soft material, and also the numerical simulations. We see an excellent agreement, excellent descriptions of the experiment by the simulation in the stiff material, but we see that we have some important quantitative differences in the soft measurements in both amplitude and width. By width, I mean to the time it decays to the residual value. Now, the amplitude and width are the essence of the slip pulses. This is how we define them. So these are important differences. What caused them? A possible reason is the frictional resistance, which should be coupled to the normal stress. At asymptotic velocity, the reduction of the normal stress is huge. There, the friction should be important. So to summarize, using detailed rupture structures characterizations, we got first conclusive direct evidence of the bimaterial coupling at the shear wave velocity. The contact area goes to 0. The variation of the normal stress is the same order of magnitude as the applied normal stress, and also we observed localizations of the particle velocities. When we compare the experiment to theory with no coupling of friction to the normal stress, we see that the singular solution describes the stiff material, but fails to describe the soft material. The simulations describe well both stiff and soft up to the shear wave velocity. Now the slip pulses at the asymptotic velocity are not well described by the simulations. Is it the result of the friction? I hope we will soon know. Do I have another minute? Yeah, I speak fast. Okay, so another place where the friction can be important is in the directionality and the velocity selections of the rupture in each propagation direction. Here are the distributions of the ruptures we got along each direction propagation. The bimaterial coupling depends also on the slip velocity, which increases with the front velocity. That means that we can get a positive feedback selecting the velocities. In the positive directions, almost all ruptures immediately accelerate towards the asymptotic velocity, because there the reduction of the normal stress is maximal, and when we take into account the friction, there we should have the most release of the normal stress. In the negative directions, we have no velocities at the shear wave velocity, where we increase the normal stress. Instead, most of the ruptures are super shear. So here also the friction, we see where it is important. So תודה רבה.
Can you tell us something about the analytic solution and the differences between the ingredients of the analytic solution and the simulation?
So actually, both of them assumes exactly the same. Just the analytical solutions assume bimaterial crack, which takes into account only the singular term, the square root singularity. The simulations solves the complete solutions. This is also where the difference in Ilya's talk about the pre-stress and the bump he showed us. So we still think that the bimaterial crack is important, but we're looking for where are the discrepancies come from.
Both have no friction.
They both don't have any friction.
But, as I recall, as
soon as you have a bimaterial interface, there's some very weird things that happen. The singularities were described by Max Williams, and they have oscillating logarithmic terms. So you could try posing them in different ways, but none of them are clearly physical. So how is it so straightforward to make these comparisons?
It's not very straightforward. The boundary conditions that they use to get this oscillating are actually zero normal stress at the interface. So it was a different problem that they solved. More than this, it is still under work. We are not sure exactly how to explain this.
Yes.
Just to clarify, the analytical solution produces force?
No, it produces bimaterial crack dominates by the singular term.
But your observation shows force.
Yeah, but the analytical solution doesn't describe
There are
our
analytical solutions for the pulses too. There are analytical solutions for the pulses.
stable solutions.
Yeah.
I thought that most of them are not stable. This is what I'm familiar with. By who? For pulse?
I'll tell you later.
Okay.
Sergio?
No, it is unclear to me how, with your experiment, you can get the negative velocity. Because
The negative.
if I understand correctly, you have a platform that is pushing this direction, and then you have something that is pushing from the top. No? That's
We share the system, yeah.
And so, if you do like this, how the cracks we can start in the negative direction?
Actually,
if you have to explain this by hand.
as also Elias thought, we can't control the nucleation process. Sometimes we get this, but we have some bias of the system that nucleates ruptures along the specific directions. So I can't flip the materials and make it propagate in the negative directions. Well, there are solutions of this. Actually, I'm not sure that I have here, but I have also a rupture.
Yeah, I understand. But
I can show you also. I'm not sure I have it. I have it here, but
Probably visit the lab.
yeah, no, I have it. Exactly what I wanted to show. When it nucleates in the middle, you actually get in the same event supershear propagation and the shear wave velocity. Okay.
Okay, so there are no more questions. Let's thank